We're beginning chapter 6, which deals with exponential functions, but before we get into section 6.1, we're going to do a quick review of rational exponents. A radical can be written as a rational exponent. So rational exponent means fraction exponent. So you see here I have a base with a fraction exponent. So the numerator and the denominator, they are specific pieces of the radical. So the denominator n is the nth root. So the nth root of a carried to the numerator's power. So carried to the m. So the nth root of a carried to the m. You can also write it like this. So we're going to start by rewriting 343 to the 2/3 as a radical and simplify. So the n is 3. So the third root of 343 carried to the m power, the squared power. So the cube root of 343 is 7, and 7 squared is 49. Alright, so let's look at another one. Let's look at writing 9 to the 5/2 as a radical. So this is the square root of 9. Notice you don't write a 2 as the second root. It's understood if there's no number there. So the square root of 9 carried to the 5th power. So the square root of 9 is 3. 3 to the 5th is 243. All right. Now we're going to write this using a rational exponent. So you see that there's a radical in this expression, so we want to go backwards and write it as fractional exponent. So this is 4 over, the base is whatever's inside the radical, so a carried to the second power, and then the root number is 7, so that goes on the bottom. Now if you will remember, rules for exponents is that you can't, well, the rule for exponents says that we can rewrite this. If the base is in the denominator, you can bring it to the numerator and just change the sign. So 4a to the negative 2/7 would be the radical 4 over the 7th root of a squared, written as a base with a rational exponent. Alright, so you guys, let's try this next one. So we have x times 5y to the 9th, but we're doing the square root. Okay, so this is the same as x times 5 to the 9/2 times y to the 9/2. So you can really rearrange this. So this is 5 to the 9/2 times x times y to the 9/2, like that. And because it's the 9/2 because there's an understood 2 right there. Alright, so that's all for the review that we're going to do. We're just going to jump into chapter 6, exponential and logarithmic functions, and we're going to focus on section 6.1, exponential functions. In this section, we will evaluate exponential functions, find the equation of an exponential function, use compound interest formulas, and evaluate exponential functions with base e. So first, let's talk about what an exponential function is. For any real number x, an exponential function is a function with the form f of x equals a times b to the x. Now notice, this is different than a power function. Power function, the base was the variable. For exponential functions, the exponent is the variable. So a is a non-zero real number called the initial value. So if there's not an a there, you understand that a is 1. B is any positive real number such that b doesn't equal 1. So any number other than 1 is positive. The domain of the function is all real numbers. So anytime you have an exponential function, the domain is all real numbers. The range is all positive real numbers if a is greater than 0. The range of f is all negative numbers if A is less than 0. So if the number here in front is greater than 0, then the range is all real positive numbers. And then if it is less than 0, it's all real negative numbers. And then the y-intercept is always 0 up to whatever the value of A is. So if A is 1, the y-intercept is 0, 1. The horizontal asymptote is at y equals 0. Okay, and so those are the characteristics of an exponential function. Okay, so let's look at this example. It says, which of the following equations represents exponential functions? So going back up here, this is the form of an exponential function. A times b to the x. So when we have these problems here with the subtraction and the addition, this would not be an exponential function. Neither would this one. However, these two, this is a base carried to an exponent, base carried to an exponent, these would both be considered exponential functions. Alright, so now let's talk about evaluating exponential functions. This is just like evaluating any regular function. You're just going to substitute the value in for the variable. So if we're finding the function at -1, we're going to rewrite the function, and wherever we see the x, we're going to replace it with -1. So now we have -4 to the 2 times -1 would be -2. So then that would be -4 to the 1, which is just -4. So you're just substituting the number in, and then you're simplifying. Alright, so let's look at this one. F at 3 for 8 times 1.2 times x, which is really 3, minus 5. Okay, so you could, oops, I wrote this wrong, didn't I? Let me fix that. Minus 5 right there. So this is really 8 times 1.2 to the -2. So let's look at our calculator, and we can do 8 parentheses 1.2 carried to the -2, and it looks like we get 5.55555. This is rounded 4 decimal places, so 5.1234. Yeah. What happens if you were doing this by hand is that 1.2 would come down because it's a negative, so you would do 8 divided by 1.2 squared. A function that models exponential growth grows by a rate proportional to the amount present. For any real number x and any positive real number a and b, such that b doesn't equal 1, an exponential growth function has the form f of x equals a times b to the x. Where a is the initial or starting value, this is going to really come in handy, so please remember that a is the initial or the starting value. And then b is your growth factor or your growth multiplier per unit x. Okay, so let's look at this example at the beginning of this section. And so when they say at the beginning of this section, if you go back and look in OpenStax, section 6.1 at the very beginning, they reference what we're about to talk about. So at the beginning of this section, we learned that the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. This situation is represented by a growth function, written down here, 1.25 times 1.02 carried to the t, where t is the number of years since 2013. To the nearest thousandths, what would be the population of India? What will the population of India be in 2038? Okay, so t is the number of years since 2013. So what we can do is we can say, okay, 2038 minus 2013, that's 25 years. Okay. Is t equals 25. So what we're going to do is we're going to substitute 25 in for t. And then we can just use our calculator. So we have 1.25 parentheses 1.012 carried to the 25th power, and it looks like we get 1.6843. Did they tell us how to round? To the nearest thousandths. So that's the third decimal place. So 1.684. So this population was in billions, so it would be 1.684 billion. All right. So let's talk about finding equations of exponential functions given two data points. So if one of the data points has the form 0a, then a is the initial value. Using a, substitute the second point into the equation f of x equals a times b to the x, and solve for b. If neither of the data points have the form 0 to the a, substitute both points into two equations with the form f of x equals a to the b to the x. Solve the resulting system of two equations in two unknowns to find a and b. Using a and b found in steps above, write the exponential function in the form f of x equals a times b to the x. All right, so a car is sold for $26,000. After 1 year, the value of the car is $16,900. Write an exponential function y in terms of the value of the car after x years if the rate of decrease is the same each year. So we start off with f of x equals a times b to the x, or y equals a times b to the x. And our initial value is 26,000. So that's our a. All right. So now they want us to substitute in a point. So it says after 1 year, the car is 16,900. So that's the point. 16,900. So what we're going to do is we're going to replace y with 16,900 equals 26,000b to the first power. It won't write. There we go. All right, so we have 16,900 equals 26,000b, because b to the first is just b. So now I'm going to divide both sides by 26,000, and we're going to find our b. So 16,900 divided by 26,000, and we get 0.65. So, rewriting our equation, y equals a b to the x, y equals a, which is 26,000, times b, which is 0.65, carried to the x. Alright, so let's try one more. A wolf population is growing exponentially. In 2011, 129 wolves were counted. By 2013, the population had reached 236 wolves. What 2 points can be used to derive an exponential equation modeling this situation? Write the equation representing the population n of wolves over time. So the first point is in 2011. We'll just call that year 0. And it's 129. And then After 2 years, 2013, that's 2 years later, is 236. So we'll use this equation here, or not this equation, this point, to write the function n of t is equal to the initial value, which is 129, times b to the t. So now we're going to substitute in 236 for n of t, and then 2 here for that. So let me just put let t be years since 2011. So now we'll divide both sides by 129. So 236 divided by 129, 1.829. And then we're going to square root both sides. We just put parentheses around that whole thing. And we're going to square root it. Oh no, here's the square root button right there. Just retype it. $1.35257. So the equation would be n of t is equal to 1.3526. I'm sorry. Let me try this again. N of t is equal to 129 times 1.3526 carried to the t power. Alright, so we're going to stop here, and we'll pick up with part 2 of the video where we will talk about compound interest.